Imagine a future where, train delays because something unexpectedly breaks down are just a thing of the past. A world where a really crucial part on a locomotive, or maybe a vital section of track, it gives you a clear heads up, maybe weeks or even months before it even thinks about failing, allowing for these perfectly timed, really efficient repairs. It sounds a bit like science fiction, doesn't it?
It does, but it's really not some distant fantasy. This is rapidly becoming a concrete reality right here, right now in the railway industry.
Welcome, curious minds, aspiring engineers, and fellow railway enthusiasts, to another deep dive. Today we're tackling a topic that's, it's absolutely foundational to the future of transportation: condition monitoring for railway maintenance. It's all about smart tech meeting these massive machines to keep our huge rail networks running smoothly, safely, and, efficiently.
Indeed. And today we're going to unpack how an ever-growing array of sensors and pretty sophisticated data analysis are completely revolutionizing the way railways manage their sprawling networks of assets. We're talking about a really fundamental shift here, moving us decisively from, reactive fixes, where you basically wait for something to break before you fix it, to a new era of proactive precision.
Right. Not just fixing, but preventing.
Exactly. And this isn't just about shaving a few minutes off a journey time, although that's part of it. It's fundamentally about enhancing paramount safety and unwavering reliability for millions of passengers and, countless tons of cargo every single day. This raises a really important question, though. How can we actually leverage these real-time insights effectively to ensure not just operational efficiency, which is key, but to uphold safety as the absolute highest priority?
That's a crucial distinction, isn't it? Safety first. So think of it maybe like giving trains, tracks, and really every piece of railway infrastructure their own advanced integrated health trackers, constantly monitoring vital signs, flagging potential issues long before they become critical. Today we'll explore what this cutting-edge technology actually is, how it's being deployed and used across the vast railway network. We'll also look at the significant challenges involved in making it truly widespread and interconnected, because that's not easy. And maybe most excitingly, how cutting-edge data analysis is truly optimizing operations, really pushing the boundaries of what's possible. So what does this all mean for the railway of tomorrow, and how will it fundamentally impact everyone who relies on it? Let's unpack this. Okay, let's start with the basics then, the foundational concept. What exactly is remote condition monitoring, or RCM? The name itself sounds quite technical, but what's at its absolute core? How does it actually work in practice?
Okay, so at its core, remote condition monitoring involves precisely what the name suggests: monitoring the health and performance of an asset from a distance. And that asset, it could be anything, really, from a tiny, intricate sensor deep inside a train's engine to a vast mile-long section of railway track. The remote aspect is absolutely key here. It means human intervention for just collecting the data is dramatically reduced or sometimes even eliminated altogether.
Right, so it's automated data collection.
Exactly. And this is achieved by strategically placing highly sensitive sensors directly on or sometimes within the asset itself, or, sometimes just very close by. And these sensors, they're not just simple thermometers or something basic. They are sophisticated instruments capable of continuously collecting vast amounts of data on a whole variety of parameters, everything from minute vibrations, acoustic signatures, temperature fluctuations, electrical currents, or even subtle physical movements and deformations. Really tiny changes.
So if I'm getting this right, it's kind of like a Fitbit for a train, or maybe even a whole network of smartwatches for every single critical component on the network, constantly sending all its vital signs back to some central hub. This real-time, continuous data flow must be a total game changer for diagnostics.
That's a fantastic analogy, actually. Yes, it perfectly captures the essence. Precisely. That capability, the remote, the continuous, and the automated monitoring, that's what enables this fundamental and truly revolutionary shift in maintenance philosophy for the entire railway industry. It's really about being proactive rather than reactive, predicting the future, in a sense, rather than simply looking back at what failed. Traditionally, railway maintenance, much like, the rigid schedule of changing your car's oil every 5,000 miles or whatever it is, or replacing your tires after a predetermined mileage, it has largely been time-based or interval-based. It's very...
Like schedules.
Right. So you would repair or replace components after a set period of time, or maybe a predetermined number of operating hours or miles traveled, regardless of their actual wear and tear. It's a very conservative approach, quite risk-averse. designed primarily to prevent catastrophic failures, which is important, of course. But often it comes at the cost of significant inefficiency. You often end up replacing parts that still have plenty of useful life left in them, simply because their scheduled replacement date arrived on the calendar.
Which means you might be prematurely retiring perfectly good equipment, essentially wasting valuable resources, labor, and time, just throwing good parts away almost. Or conversely, and this seems perhaps even worse, something might fail before its scheduled maintenance. If it experienced unusually heavy use or unexpected stresses, or maybe even a manufacturing defect slip through, that seems incredibly inefficient from a resource perspective and potentially very unsafe too. You're either over-maintaining or under-maintaining, never quite hitting that sweet spot of optimal intervention. It's a bit hit and miss.
That's exactly where condition-based maintenance, or CBM, comes in. And it's the paradigm shift we're really talking about today. Instead of those fixed, often somewhat arbitrary intervals, intervention is based directly on the actual real-time condition of the asset. As determined by that continuous stream of data coming from the RCM systems, it's about maintaining components only when they show verifiable, data-driven signs of needing it.
Okay, so the data tells you when to act.
Precisely. Not just because a calendar or a mileage counter dictates it. For instance, if a wheel bearing is showing slight but consistent signs of increased vibration, or maybe a subtle temperature rise that wouldn't normally be picked up, CBM can flag it for immediate inspection or replacement before it becomes a serious disruptive or dangerous problem, without waiting for a scheduled overhaul that might be months away. This isn't just about reacting to a fault. It's about predicting it with real precision.
That makes sense. Proactive, data-driven.
And this approach, it leads to really profound efficiencies. It drastically reduces unplanned downtime, which is a huge cost and disruption factor. And critically, it elevates safety to an unprecedented level. Consider the ambitious sort of collective vision for the railway industry in 2040. There's this goal, this statement. A world where unplanned maintenance and damage to track and train are minimized through enhanced industry-wide condition monitoring.
Wow, minimize. That's a strong goal.
It is. And this isn't merely some hopeful dream or a vague aspiration written down somewhere. It's a strategic, industry-wide objective. It actively permeates discussions, it directs research funding, and it shapes massive investment plans across the entire sector. It's about building inherent resilience, predictability, and ultimately absolute trust into the very fabric of the railway system itself.
And the impact of this shift isn't just theoretical, is it? Or some abstract strategic goal in a report. It translates into truly tangible, real-world value. Value that affects everyone, from passengers trying to get to work to freight companies moving goods across the country. We're talking about massive financial and operational benefits here.
Absolutely. And the numbers involved are quite compelling because they really highlight the sheer scale of the potential impact. Independent research has estimated a potential reduction of a staggering 15% in delays across the entire network, if RCM were effectively and broadly deployed throughout the industry. 15%.
15% reduction in delays, that's enormous.
It is, and when you put a financial figure on that, it translates to an estimated value of around 90 million per year, just in the UK context.
90 million pounds a year.
Think about the cumulative impact of fewer delays. Passengers reach their destinations on time, freight moves efficiently, supply chains aren't disrupted. The ripple effect on the national economy is profound. That is not a small number. It's a significant figure that underscores the immediate, powerful financial incentive for adopting and scaling these technologies.
90 million pounds a year, just from reducing delays through better maintenance. That's a huge number, not just theoretical, but a concrete, measurable improvement that affects everyone using the railways.
And what about sharing that valuable data? Does keeping condition monitoring data locked away in isolated silos reduce its overall value, or does collaboration actually amplify it?
That's a great question. And what's truly fascinating here is that even a portion of that enormous 90 million figure, specifically around 12 million per year, that portion is derived solely from simply sharing RCM data across different industry boundaries.
Just from sharing, 12 million. Yes. It highlights the immense power of collaborative intelligence, the network effect of data. The railway industry is inherently fragmented, right? You have different train operating companies running the trains. You have separate infrastructure managers like network rail owning and maintaining the tracks, and then various manufacturers supplying the rolling stock and equipment.
Lots of different players.
Exactly. And historically, each might collect its own data, often in its own format, but rarely share it seamlessly with the others. But when train operators, infrastructure managers, and rolling stock manufacturers can share condition data seamlessly, securely, and ideally in a standardized format, they gain an incredibly holistic view of the entire system. It's like putting together a puzzle with pieces from different boxes.
Right, you see the bigger picture.
Precisely. Imagine a scenario. Maybe a subtle fault identified by a trackside sensor could directly inform a specific train's future maintenance schedule by predicting increased wear on its wheels because of that track section. Or, conversely, data from a train's internal diagnostics about its braking system might reveal a developing issue with a specific section of track that's causing unusual stresses on multiple trains.
Ah, I see. The train data informs the track maintenance and vice versa.
Exactly. This cross-pollination and integrated analysis of data amplifies insights exponentially. It allows for more coordinated, efficient interventions far beyond what any single entity could achieve operating in isolation. It's really about breaking down those traditional silos of information, fostering a truly interconnected railway ecosystem, and unlocking value that was previously just unattainable.
That makes perfect sense. More data shared equals smarter decisions overall.
So where is RCM actually being used right now? Is it just on the trains themselves, or are we talking about the tracks, the signaling systems too? It sounds like it could be, well, pervasive throughout the entire railway ecosystem. It is already widely deployed, and its application is expanding rapidly across the entire network, not just in isolated pockets or pilot projects anymore. Modern trains, for example, utilize RCM extensively to monitor the condition of a myriad of critical onboard components. This includes high-usage, safety-critical items like passenger doors, think how many times they open and close daily, the intricate systems that control braking, ensuring precise stopping power, are heavily monitored. The health of wheel bearings, which are constantly subjected to immense forces, and the complex traction systems that actually propel the train itself, all under constant scrutiny.
And this data gets reported back how?
This operational and condition data is typically reported directly by the train's own sophisticated train management system, or TMS. It acts like the train's central nervous system, constantly sending updates on its health and performance back to a control center or depot.
Okay, so the train monitors itself. But what about the track and signals?
But you're absolutely right, it's not confined to just the trains. The fixed railway infrastructure itself also has extensive RCM systems in place. These are often focused on safety-critical assets fundamental to the operation and integrity of the network. A prime example is points, machines, those crucial, complex mechanical mechanisms that physically switch trains from one track to another, allowing routing and flow. Monitoring their health and precise operation is absolutely vital.
Vital to prevent derailments, I mean.
Exactly, and to ensure smooth network throughput. Similarly, the complex signaling systems, which are essentially the traffic lights and sophisticated brains governing all train movement, they are heavily monitored too. Any anomaly in these systems can lead to massive disruptions or, more importantly, severe safety hazards. So continuous RCM is paramount for maintaining system integrity and passenger safety.
It sounds like there's this whole interconnected web of monitoring happening, almost like a digital nervous system for the entire railway, as you said. How do we even begin to categorize all these different RCM systems? It feels like it could get overwhelming with so many sensors and so much data coming from every direction.
That's an excellent question, and it can seem complex. To simplify this vast landscape, we can think of it in 4 key quadrants. It's a useful framework. These quadrants effectively represent the distinct relationships between who or what is doing the monitoring and what is specifically being monitored. It helps organize the diversity of RCM applications.
Okay, 4 quadrants. What are they?
First, we have trains monitoring trains. This quadrant primarily involves a train's internal systems assessing the health and performance of its own components. It's essentially the train taking its own pulse, doing an internal health check.
Got it. Train self-checks.
Second is trains monitoring infrastructure. Here, sensors or highly specialized equipment mounted directly on a train are actively looking at the condition of the track beneath it, or the overhead electrical lines above it as the train moves along. In this scenario, the train itself essentially becomes a mobile sensor platform, gathering data about the environment it's traveling through.
Interesting. The train as a roaming inspector.
Third, we have infrastructure monitoring trains. This is where fixed trackside sensors, strategically placed along the network, assess aspects of passing trains. They often focus on critical components like wheel health, checking for defects like wheel flats or overall integrity or the condition of their axles. These are static checkpoints assessing moving assets.
Okay, trackside checks on the trains as they go by.
And finally, the fourth quadrant is infrastructure monitoring infrastructure. This focuses entirely on fixed track assets, monitoring other fixed track assets. Think of one part of the static railway system keeping a watchful eye on another part. Each of these quadrants contributes unique and vital data, and when you combine them, they offer a truly comprehensive understanding of the railway network's overall health and operational status.
That categorization really helps clarify things. Quadrant 1, train on train. 2, train on infrastructure. 3, infrastructure on train.
Right.
4, infrastructure on infrastructure. Makes sense. Can you give us some specific concrete examples for each of these? What kind of actual data are we talking about, and how is it collected to generate these insights?
Certainly. So for trains monitoring trains, quadrant 1, you have the sophisticated train management systems, TMS themselves, integrating data from various onboard sensors for that holistic view. Beyond that, there's dedicated axle bearing monitoring. Miniature sensors embedded right into the axle boxes constantly check for temperature spikes or unusual vibrations, early indicators of a failing bearing, a critical safety concern.
Tiny sensors doing a big job.
Absolutely. And then there's ride or stability monitoring, which uses accelerometers placed within the train carriage to assess the smoothness of the ride. This can indirectly reflect issues with the train's bogies or even subtle irregularities in the track itself, giving an early warning.
Okay, so that covers train self-monitoring. What about quadrant 3, infrastructure monitoring trains?
Right. When infrastructure monitors trains, we see technologies like wheel impact load detection or WILD systems. These use specialized sensors embedded in the track to measure the force exerted by train wheels as they pass over. High-impact loads can indicate defects like wheel flats or out-of-round wheels that could damage the track, or worse, lead to derailment.
Measuring the punch the wheel gives the track.
Exactly. There are also trackside acoustic axle bearing detectors. These use an array of microphones to literally listen for anomalies, unusual grinding sounds from passing wheel bearings that might signify degradation before they overheat.
Listening for trouble. Clever.
And a classic yet still vital example is the hot axle box detector, or HEBD. It uses infrared sensors to check for overheating bearings as trains pass by, a crucial safety measure to prevent catastrophic failures and potential fires.
That real-time assessment of moving trains sounds incredibly powerful. What about the other way around? Quadrant 2, when the trains themselves are the sensors, monitoring the infrastructure they're traveling on. That trains monitoring infrastructure concept is particularly fascinating.
It is indeed, and it's a rapidly growing area. For trains monitoring infrastructure, quadrant 2, we have highly specialized measurement trains. These aren't regular passenger trains, but dedicated vehicles kitted out with advanced arrays of lasers, cameras, and ultrasonic transducers. They perform detailed track geometry measurement using precise laser scans to assess rail alignment, the gauge that's the distance between the rails and twist, subtle deformations that can affect ride quality and safety.
So dedicated inspection trains.
Yes, but the tech is moving towards using operational trains, too. These specialized trains also carry ultrasonic measurement systems that use sound waves to detect internal rail flaws, like hairline cracks invisible to the eye, but which can grow and cause dangerous rail breaks. And overhead line measurement systems ensure optimal contact between the train's pantograph and the electrical line, crucial for consistent power supply and avoiding wear or damage to the overhead system.
Okay, and the last one, quadrant 4, infrastructure monitoring itself.
And finally, infrastructure monitoring infrastructure, quadrant 4. This includes advanced points condition monitoring, specifically for those critical track switches we discussed earlier. These systems assess the operational health, precise alignment, and subtle movements of the points mechanisms themselves. Rail temperature monitoring systems keep a constant eye on thermal expansion and contraction of the rails. This is critical to prevent dangerous track buckling in extreme heat or potential rail breaks in freezing conditions.
Buckling track is a major hazard.
A huge hazard, and signaling status monitoring continuously checks the operational state of traffic lights, track circuits, and other signaling equipment, ensuring they are functioning correctly and providing accurate information to train drivers. Each of these systems collects very specific, targeted data, and when combined, they contribute to that holistic, extremely detailed view of the network's health and potential vulnerabilities.
That trains monitoring infrastructure concept, quadrant 2, is really interesting. So a regular train, just running along the track can actually tell us about the track's condition just by how it moves or vibrates,
Right.
without needing specialized measurement equipment every single time. How does that actually work?
Exactly. There's a lot of cutting-edge research and increasingly deployment being done on the feasibility of using acceleration data measured inside a regular operational vehicle. So basically, how the train is vibrating and moving as it goes along the track to detect and categorize the severity of track faults, or even assess the overall track quality.
Like using the train's feel of the ride.
Sort of, yes. Think of it like a subtle tremor indicating an issue with the foundation, even if the building itself looks fine from the outside. But it's much more sophisticated than just feel. This isn't a simple process, though. You can't just slap an accelerometer onto a train and call it a day. It requires incredibly detailed vehicle track dynamic modeling.
Modeling. What does that involve?
Well, this modeling is crucial because it helps engineers understand precisely how the train interacts with the track under various conditions, how its suspension responds, how different speeds affect vibrations, and how specific track defects manifest as unique motion patterns in the train. This deep understanding then supports critical decisions on sensor selection and placement within the vehicle. Where is the absolute best place to put an accelerometer to pick up vibrations specifically related to track issues, while filtering out the train's own operational vibrations, like from the engine or auxiliary systems?
Filtering out the noise.
Exactly. It also drives the development of highly efficient and intelligent algorithms. These are like complex mathematical recipes designed to process the massive quantities of acceleration data collected in real time. We're talking potentially petabytes of information. These algorithms meticulously filter out the noise of normal operation to extract the subtle yet meaningful signal of track defects. This requires a significant leap in computational power and analytical sophistication.
So it's a really sophisticated engineering challenge behind the scenes, far more than just installing a sensor and reading the output. And is this technology currently in widespread use, or is it still largely in the R&D phase?
It has definitively moved beyond just the research lab. It has undergone rigorous trials on network rail measurement trains, those dedicated vehicles we mentioned earlier, specifically designed to assess track conditions with extreme precision. But more importantly, it is currently being trialed on a number of operational fleets on the GB rail network, so integrating these capabilities into the everyday operation of regular passenger and freight trains.
So it's happening now on regular trains.
It's being trialed, yes. This signifies a monumental step from proof of concept to real-world application. The ultimate goal is to make every train an active, intelligent sensor platform contributing to the health of the entire network.
Okay, what about those critical points and crossings we mentioned earlier, the S&C, or switches and crossings? Those complex bits of track. How is infrastructure specifically monitoring those parts, given their importance?
Right. Switches and crossings, S&C, are indeed among the most complex and highly stressed parts of the track system. They are intricate mechanical assemblies where rails converge or diverge, allowing trains to change tracks. Because they involve multiple moving parts, heavy forces, and constant wear, they are prone to unique types of degradation and often account for a disproportionate number of track faults. They're a real focus area.
A known weak point, in a way.
A known high stress point, definitely. So, to address this vulnerability, specialized sensor technologies have been developed specifically for monitoring and detecting degradation in these critical areas, providing targeted insights where they are most crucially needed. A particularly innovative and, I think, elegant example of this is something called the smart washer.
A smart washer, like for nuts and bolts.
Exactly. Imagine a standard washer, that small, unassuming disc that typically goes under a nut to distribute the load of a bolted joint. Now, miniaturize and embed sophisticated sensors directly into that tiny component. These smart washers are designed for critical bolted joints, like those found on rail stretcher bars that keep the rails precisely aligned at S&C points.
Okay, so what can this tiny washer tell you?
This tiny component can locally and remotely monitor crucial parameters. It measures the clamp force holding the joint together, indicating if the bolt is loosening, a major cause of misalignment and potential failure. It monitors temperature, which can signal excessive friction or unusual wear, and it even tracks its orientation, ensuring the joint hasn't shifted or twisted unexpectedly. This granular data is then transmitted wirelessly to a remote monitoring system, providing continuous, microscopic insight into the integrity of a fundamental structural connection, vital for track safety.
That's incredibly clever. A tiny seemingly insignificant component providing such critical data that could prevent a major failure. It really highlights how detailed and granular this monitoring can get, down to the level of a single bolt's tightness.
Indeed. It's a testament to the innovation happening in this field. And further work is also investigating the feasibility of monitoring other typical S&C defects beyond just bolt integrity. This involves detailed S&C modeling. Engineers use sophisticated computer simulations to predict the typical ranges of forces, displacements, and accelerations that occur during train movements through these complex sections.
And simulating the stresses.
Precisely. This meticulous modeling helps identify where and how different types of defects are likely to manifest under various operational scenarios. Crucially, it informs the optimal selection and placement of additional sensors throughout the S&C network to specifically capture those unique degradation patterns. It's about putting the right sensor in precisely the right place to catch the exact problem you're looking for, often before it's even noticeable to the human eye.
Right. Targeted sensing based on predicted failure modes. Now, beyond the continuous real-time monitoring we've been discussing, are there ways automation is changing how we perform physical inspections of components? Moving beyond manual checks that can be time-consuming and, let's face it, maybe a bit subjective.
Absolutely. We're witnessing a significant and transformative shift towards enhanced automated non-destructive testing, or NDT, techniques. For those perhaps less familiar, NDT refers to inspection methods that allow you to assess the health and integrity of a component without causing any damage to it. Think X-rays, ultrasonics, that kind of thing.
Checking without breaking.
Exactly. And while NDT has long been foundational in engineering, what's truly innovative now is the automation and integration of these techniques into real-time condition monitoring systems, moving from manual, sporadic checks done by a person to continuous or near-continuous automated assessments performed with unprecedented speed and precision.
So machines doing the NDT checks automatically.
Yes. Think of depot-based systems that can automatically inspect key components as a vehicle simply moves through a designated inspection lane, like a high-tech drive-through. This includes highly precise systems that can measure wheel profile wear, assessing the exact shape and integrity of the wheel as it rolls by, identifying even subtle deviations. Other systems automatically assess brake wear using optical or laser measurements to quantify material loss without physical contact. And increasingly sophisticated image profiling and pattern recognition technologies are being deployed. These use high-resolution cameras and advanced algorithms, often powered by AI.
AI spotting problem.
It's essentially, yes, to spot anomalies like hairline cracks, chips, unusual surface textures, or unexpected wear patterns on various components, comparing them instantly against millions of ideal profiles stored in a database. This significantly helps reduce the reliance on manual, time-consuming, and sometimes subjective human inspections. It leads to far more consistent, reliable, and rapid defect detection at scale.
So trains essentially get an automated, comprehensive health check while they're just passing through a depot or a designated inspection point. Almost like an automated car wash, but for diagnostics. That must streamline things immensely.
Exactly. That's a great way to put it. And it extends even further out onto the network itself. For instance, specialized ultrasonic inspection trains are now replacing traditional manual ultrasonic measurements and visual inspections for detecting internal flaws in the rails themselves.
Instead of someone walking the track.
Precisely. Previously, a technician would literally walk along the track with a handheld ultrasonic device. Very labor-intensive, slow, limited by human endurance and maybe subjective interpretation. Now, a train equipped with an array of ultrasonic transducers can scan hundreds of miles of track much faster, more comprehensively, and with far greater consistency. We also have automated scanning of wheel rail damage. This uses advanced imaging and laser profiling to replace visual inspections, offering far greater consistency and detail in identifying even subtle surface damage or fatigue that might be easily missed by the human eye.
So it's all about speed, consistency, precision, and the ability to cover these vast networks at scale.
That's the core benefit, yes. Removing human limitations and subjectivity where possible.
Okay, all this sounds incredibly promising, like a truly transformative leap for the railway industry. But, and there's usually a but, with such a complex and interconnected system involving vast amounts of data, diverse stakeholders, legacy infrastructure mixed with new tech, there must be significant challenges in implementing RCM widely and effectively. What are the big hurdles right now that the industry is really grappling with?
You're absolutely right. It's not without its challenges. There are indeed significant hurdles that need to be systematically addressed for RCM to reach its full potential across the board. One key area, which sounds deceptively simple but is incredibly complex in practice, is the accurate identification of the actual asset being measured.
Knowing exactly which part the data is coming from.
Exactly. Imagine you have hundreds of thousands, maybe millions of components across an entire rail network. Individual brake pads, wheel sets, complex signaling units, miles and miles of track sections, all generating data. Ensuring that you know precisely which specific component or vehicle a particular sensor reading belongs to is crucial, especially with the increased use of automatic vehicle or component identification and tagging systems like RFID. If data comes in without clear lineage or precise asset tagging, if you don't know exactly which wheel bearing generated that temperature alert, it becomes very difficult to accurately track degradation over time for that specific bearing.
Yeah, you can't build a history for it.
Right. You can't schedule targeted maintenance for the right part or even build a reliable historical performance record for that specific asset. Data without clear lineage, without that unique ID properly attached and tracked, is effectively useless for targeted intervention. It's just noise.
So it's like making sure the right medical record gets tied to the right patient and not just broadly to someone in the hospital. Without that precise identification, even perfect data becomes pretty meaningless for predictive maintenance. What else poses a significant barrier?
Another major challenge lies in cross-industry data sharing and developing common information architectures and protocols. We touched on this earlier regarding the value of sharing. As we discussed, the railway industry is highly fragmented. Different operators manage trains, separate infrastructure managers own and maintain the tracks, various manufacturers supply the rolling stock and equipment.
All those different players again.
Exactly. And each of these stakeholders often has their own proprietary systems, their own unique data formats, their own specific protocols for collecting, storing, and analyzing information, legacy systems mixed with new ones, getting them all to speak the same digital language, to standardize data inputs and outputs, and to share data seamlessly, efficiently, and securely. That is a truly complex undertaking. It involves not just technological hurdles, getting different IT systems to talk to each other, but significant organizational, commercial, and even legal challenges.
Yep.
Who owns the data? Who pays for the sharing infrastructure? What are the security implications?
Right, it's not just a technical problem.
Not at all. And if we connect this back to the bigger picture, this persistent lack of standardized data protocols severely limits the industry's ability to maximize that 12 million pound per year value we discussed earlier, the value specifically derived from sharing RCM data across industry boundaries. When valuable data remains siloed within individual companies or departments, the immense insights that could be gleaned by combining information from different parts of the system are simply lost. This fragmentation inhibits a truly holistic, whole system view of the network's health and prevents optimized, coordinated maintenance across the entire rail ecosystem. It means we're constantly trying to solve a puzzle with half the pieces missing.
Okay, so asset identification is challenge one. Data sharing and standardization is challenge two. What's the third big one? Even if you manage to collect all this data perfectly tagged and somehow get everyone to agree to share it in a common format, how do you actually make sense of it all? It seems like it could just become an overwhelming flood of raw numbers, a data deluge that could just swamp decision makers rather than help them.
That's the third major challenge, and arguably the most crucial one. The effective use of condition monitoring and inspection data once it's collected and made accessible. You hit the nail on the head. It's simply not enough to gather vast quantities of data. You need the sophisticated tools and the human expertise to apply intelligent data analytics to support real-world maintenance decisions and optimization. This requires moving beyond simple dashboards showing current readings. It means leveraging advanced techniques, often employing machine learning and artificial intelligence, and crucially cultivating specialized expertise. Data scientists who understand railways, railway engineers who understand data science.
Bridging that skills gap?
Precisely. To extract meaningful, actionable insights from what can be truly massive, complex, and sometimes noisy data sets. Without these robust analytical capabilities and the skilled personnel to interpret them, you're essentially sitting on a mountain of invaluable information but lacking the map to navigate it or the tools to mine its gold. The ultimate goal is to move from mere data collection to insight generation and, most importantly, to actionable intelligence that directly impacts and improves operations.
So it seems like the key to overcoming these challenges and unlocking the true potential of RCM lies in making better, smarter, more intelligent use of the data, especially with advanced analytics. How does that translate into tangible, real-world maintenance improvements for railway operators and, ultimately, for all of us who rely on the network?
You've hit on the critical point there. Advances in automated NDT and RCM techniques now provide this unprecedented opportunity to accurately and continuously monitor component condition. But as you rightly pointed out, the true power comes from intelligently trending this data over time. Observing its behavior, discerning patterns and trajectories, that this isn't just about spotting a single anomaly in a moment, it's about understanding the life story of a component and predicting its future chapters based on how it's behaving now.
Seeing the trend, not just the snapshot.
Exactly. And this intelligent trending allows us to do several powerful things. Firstly, it helps identify rogue components or vehicles. Imagine a specific wheel set that consistently shows higher than average wear rates compared to others on the same route, or a particular train carriage whose passenger doors frequently report minor but escalating faults, even when identical doors on the same train are performing perfectly.
The outliers.
Right. Intelligent trending can pinpoint these rogue assets that are degrading faster than expected or behaving anomalously. This allows for targeted intervention on that specific part before a widespread problem develops, or it causes a cascading failure elsewhere. Secondly, this analysis enables us to quantify component degradation rates and accurately predict residual life.
Okay, knowing how fast it's wearing out and how long it's at left.
Precisely. This means we can understand how fast a particular part is actually wearing out, not just theoretically based on its design specifications, but based on its real-world operational data under specific conditions on specific routes. From this, we can predict, with a reasonable degree of confidence, how much useful life it truly has left before it's likely to fail or require intervention. This is a complete game changer for maintenance planners and engineers.
I can imagine.
And thirdly, armed with this truly predictive power, we can develop highly accurate predictive maintenance plans. This is the ultimate shift we've been talking about. Moving beyond reactive fixes, waiting for a breakdown, or those rigid time-based schedules, replacing parts too early, potentially, to scheduled interventions based on forecasted, data-driven needs. You replace a part only when the data indicates it's truly nearing the end of its useful life, maximizing its utilization, minimizing waste while maintaining paramount safety.
So it's about shifting from knowing what happened in the past, the failures, the repairs, to predicting when something might happen in the future with a very high degree of confidence. That completely changes the maintenance game, doesn't it?
Yeah.
Transforms it from a reactive scramble into more of a strategic chess match.
Exactly. That's a great way to put it. While current railway maintenance often operates as a blend of corrective maintenance reacting to a fault after it occurs, often leading to unplanned disruptions in costs and scheduled fixed interval maintenance. The selection of the optimum strategy between these two approaches has historically been, well, quite subjective.
Based on experience, maybe gut feeling.
Often, yes. Based on historical aggregated data, maybe rules of thumb passed down, or the invaluable but sometimes unquantifiable experience of expert engineers. Which is important, but it can sometimes lack robust scientific proof or be economically inefficient in the long run. Research now is intensely focused on realizing the full potential of this condition monitoring data to really support maintenance decisions and optimization. Making that selection between fix now, fix later, predict and fix far more scientific, objective, and economically sound.
Using data to prove the best approach.
Exactly. This means a deeper investigation into using a condition-based maintenance CBM approach to develop the most suitable solutions for both predictive and even optimized corrective maintenance scenarios. It involves asking questions like, when is it truly best to proactively replace a part based on its predicted degradation rate? And when is it actually acceptable, safe, and maybe even more efficient overall to wait for an early fault code and then react quickly with a planned intervention?
Finding that optimal balance.
Right. And this also involves actively building on the extensive experiences and proven knowledge of CBM techniques applied successfully in other industry sectors that have faced similar challenges with complex, safety-critical assets. Like the aviation industry, which has been a real pioneer in predictive maintenance for decades. The underlying principles, monitoring, analyzing, predicting, are highly transferable, even if the specific assets and operational environments are different.
What's truly fascinating here is that it's about applying foresight, not just hindsight. It's no longer just meticulously recording failures and fixing them after the fact.
Yeah.
It's actively trying to prevent them before they even become an issue, which has to be a dream for anyone involved in operational efficiency and reliability.
Precisely. It's the intelligent analysis of condition data, to identify those subtle trends and predict component degradation or even imminent failures before they occur. And this isn't theoretical conjecture anymore. It has already been demonstrated as feasible and highly effective on a wide range of actual vehicle components within various cutting-edge research projects and pilot deployments. It's proving its efficacy in real-world railway applications.
So the proof is there.
The proof of concept is absolutely critical for driving widespread adoption across the industry, showing that it works and delivers value.
That's incredibly powerful. Can you break down the specific benefits we gain by fully embracing this condition-based maintenance CBM approach, specifically for rolling stock the trains themselves? What tangible advantages does it offer over traditional, less informed methods?
Okay, yeah. The benefits of fully embracing CBM for rolling stock are quite clear, compelling, and genuinely transformational. Firstly, CBM enables us to automatically measure the condition of key components with an unprecedented level of detail and consistency. We talked about automated NDT. This is a massive leap from traditional manual measurements, which, let's be honest, can often suffer from poor repeatability. Different technicians might get slightly different readings on different days.
Human variability.
Exactly, and lower accuracy due to human error, maybe limitations of the manual tools used, or simply the difficulty of accessing certain components in a timely or consistent manner. Automated systems provide consistent, objective, and often exquisitely precise data, removing that human variability factor. Secondly, CBM systems process the raw sensor data directly to determine component conditions. This eliminates potential human interpretation errors at that initial stage of data analysis.
The machine interprets the raw data first.
Yes. The system intelligently interprets the sensor input, identifies complex patterns, and directly converts that raw data into a clear, unambiguous assessment of the component's health status. This allows for user-configurable alerts and reports based on absolute measurements, meaning based on objective, quantitative data points, and, most crucially for planning, provides that precise prediction of residual life. So instead of a vague feeling of something might be wrong with that bearing based on intuition or a quick check, you get specific data-driven insights. Insights that say, based on current vibration trends and temperature readings, this specific bearing has approximately X operating hours or Y days left before it likely needs attention, given its current degradation rate.
So you get a clear, data-driven warning, and you know exactly how much time you have to plan the intervention. That sounds like an absolute dream for maintenance planners. Moving them from constant crisis management to strategic resource allocation, where every repair is planned for optimal efficiency.
It absolutely does. It fundamentally changes the nature of their work, moving it towards strategy rather than just reaction. It significantly supports decision-making and empowers maintenance planning like never before. You can now target maintenance based on the actual condition or the predicted residual life of a specific component, rather than being forced to adhere to an arbitrary fixed schedule that might lead to premature replacements or, worse, unexpected failures. This means you only service a component when it genuinely needs it, maximizing its operational life, minimizing unnecessary downtime, and crucially, reducing the cost of replacing parts that are still perfectly functional. It optimizes both efficiency and expenditure across the board.
Speaking of maintenance optimization,
Yeah.
You mentioned looking at other industries for inspiration, particularly aviation. What specific insights are we drawing from, say, the airline industry to apply to railway maintenance, given their long history with complex, safety-critical systems and, frankly, the huge cost if things go wrong?
That's a very relevant comparison. A key methodology being studied and meticulously adapted from the aviation industry is the Maintenance Steering Group methodology, usually known as MSG3. This provides a highly structured, systematic, and incredibly rigorous framework for developing optimized, scheduled, condition-based maintenance programs. Aviation has faced challenges with safety-critical components, complex interconnected systems, and the astronomically high cost of downtime for decades. MSG3 was originally developed to optimize their maintenance practices by focusing laser-like on preventing functional failures before they happen.
A structured way to decide what maintenance to do and when.
Exactly. This framework, which has been outlined in specific railway research and adaptation documents, describes suitable techniques to support truly data-driven maintenance specifically for rail. It focuses intently on how to diagnose and identify potential system failures from the wealth of condition monitoring data being collected, and subsequently, how to use that data not just to identify a fault that's happened, but to strategically support maintenance decisions and planning, ensuring interventions are both necessary and timely and efficient.
How is this applied in practice to trains?
This robust approach is then applied directly to specific rolling stock components within the unique railway context. For example, assessing data from onboard train management systems to identify and predict faults in complex systems like brake control units or those sliding doors, which are crucial for both operational safety and smooth passenger flow. It also involves assessing individual wheel set condition and combining that with broader train operational data like the road it runs, typical speeds, average load factors to further improve maintenance planning. This comprehensive approach takes into account real-world operational constraints like train schedules, depot availability, technician rostering, allowing for maintenance to be performed during optimal windows rather than reacting to an emergency breakdown.
That sounds like a very thorough and logical process. Can you give us a quick, simplified overview of what an MSG3-like analysis would actually entail for a typical railway component? How do you break down the problem to get to that optimized maintenance plan?
Okay, at a high level, an MSG3 analysis is a systematic, almost hierarchical way to determine the optimal maintenance tasks for complex systems or components. It forces a deep understanding of the asset. It involves several key steps. First, you meticulously identify the functions of a component. What exactly is it designed to do? Be really specific. Then, you pinpoint what constitutes a functional failure. How does it fail to perform its intended function? Not just what breaks, but what prevents the system from doing its job properly. Next, you rigorously analyze the effects of that functional failure. What happens if it fails? What are the safety implications, the operational knock-on effects, the economic consequences? And crucially, what are its underlying causes? Why does it fail in the first place? Detailing every potential failure mode you can think of.
Understanding the what, the how bad, and the why.
Precisely. Once these foundational elements are understood with extreme clarity, you use a sophisticated decision logic, a kind of structured flowchart, to select the most appropriate maintenance actions. There are different levels of analysis within MSG3. Level 1 analysis evaluates the consequence of the failure. Is it a safety failure, highest priority, an operational failure, disruptive, or primarily an economic failure, costly but less critical? This classification helps prioritize. Then, Level 2 analysis uses that consequence rating to select the specific type of maintenance task. Is it a task to prevent the failure from occurring in the first place, or to detect it early before it becomes serious? Or perhaps, for minor failures, simply to allow it to fail and then fix it because the consequences are minimal and prevention is too costly.
So the consequences drive the type of action.
Exactly. And the whole process includes vital feedback loops from in-service data, real-world performance information, and continuous input from operators and maintainers on the ground. This iterative, data-driven feedback is used to continually refine and improve the maintenance program, ensuring it remains optimized for critical items throughout their entire operational life. It's about constant learning and adaptation, not a one-off analysis.
This sounds like a really robust, living framework, not just set in stone. How does this connect with the diagnostic data trains are already collecting out there in the field, the raw material that fuels these kinds of analyses?
That's an excellent point, as it brings the theoretical MSD3 framework into direct contact with real-world operational data streams. Modern rolling stock are indeed already equipped with highly sophisticated onboard diagnostic systems that regularly generate vast quantities of operational and condition data. These systems are constantly monitoring hundreds, maybe thousands of parameters.
All that data the TMS collects.
Right. What's fascinating here, though, is that often this data comes in the form of simplified event data. Things like specific fault codes, error 402, door motor overload, or warning, brake pressure low, or info, traction system interruption detected. Or it might be specific measured variables captured only for a particular event, rather than continuous raw sensor time series data, which would be those uninterrupted streams of readings like vibration amplitudes measured thousands of times per second.
So it's more like specific alerts or snapshots.
Often, yes. More distilled and aggregated. But despite being simplified, this event data is still incredibly valuable, especially when you aggregate it over time and across many vehicles. Diagnostic data has been specifically collected from major industry projects, like the Impact T2 project you mentioned, which involved significant collaboration with key industry partners like DB, Siemens, and CHEF. This extensive collaboration has allowed for the collection of rich data sets for a wide range of critical systems, including brake control units, traction control units, and those sliding doors we keep mentioning. This real-world diagnostic data provides the raw, living material for applying the advanced analytical methodologies and MSG3-like frameworks we're discussing. It's about turning those operational events into predictive insights.
Okay, so you have these diagnostic codes and event logs streaming in from potentially thousands of trains across the network. How do you actually turn that potential mountain of event data into actionable insight for preventing failures. What's the precise methodology for processing this kind of diagnostic data to unlock its predictive power?
Right, processing that event data effectively is key. The general methodology for doing this, moving from those raw, seemingly disparate events to concrete predictive insights, includes several key systematic steps that build upon each other. First, there's the crucial selection of relevant diagnostic codes. This isn't just about grabbing every single fault code the train generates. That would be overwhelming and include a lot of noise. It's a highly targeted process. This selection is primarily guided by the invaluable practical experience and deep institutional knowledge of depot staff and maintenance engineers. They know from experience which specific codes or events typically precede actual maintenance intervention.
They know which codes matter.
Exactly. They can help filter out the codes that usually indicate a real underlying problem rather than just a transient, self-correcting anomaly. The selection process also meticulously considers the design of the onboard diagnostic system architecture itself, particularly for safety-critical components, where even minor or infrequent indications might be absolutely crucial and cannot be ignored. We then meticulously analyze the frequency of these selected codes and investigate their relationships. For example, does fault code A often appear shortly before the more serious fault code B, suggesting a cascading issue or an early warning sequence we can leverage.
Looking for patterns between codes.
Yes. Then second is the statistical analysis of diagnostic codes. Once relevant codes are identified and contextualized, we dive deeper into their behavior over time. This involves looking at the raw frequency of occurrence. How often does a particular fault code appear over a given period, say per 1,000 miles? We also track how long a fault code was active for each time it occurred. This gives an indication of the severity or persistence of a problem. Was it a momentary glitch or a sustained issue? Crucially, we analyze cumulative patterns. Does a specific code occur with increasing frequency over time as a component degrades? Or does its average activation period lengthen? These trends are vital. We also rigorously investigate relationships between different diagnostic codes and other measured variables recorded at the same time to understand underlying systemic issues. For instance, does a particular door fault code consistently coincide with a specific voltage drop reading, suggesting an electrical root cause, or an increase in ambient temperature, indicating an environmental factor might be triggering it?
Connecting the dots between different data points.
Precisely. Third is the forecast of future activations. This is where the real predictive power comes in, moving beyond just observation of the past to genuine foresight. Using various advanced analytical techniques, things like linear or nonlinear regression, which identify trends and correlations in historical data to predict future behaviors, or even more advanced neural networks.
Neural networks, that sounds complex.
They are a powerful form of artificial intelligence, yes, capable of learning incredibly complex, non-obvious patterns within massive data sets. Think of them as highly sophisticated pattern recognizers. They can find relationships that even a human expert analyzing spreadsheets might miss, allowing for potentially unprecedented accuracy in predicting when a specific diagnostic code might appear again, or when a system might reach a critical threshold where failure is deemed imminent.
Using AI to predict the future faults.
In essence, yes. And fourth, the ultimate practical goal of all this meticulous forecasting is to provide early warning of imminent failure. By accurately predicting potential issues, often weeks or sometimes even months in advance, this allows maintenance teams to plan interventions proactively. This is that fundamental and revolutionary shift away from costly, disruptive, and unscheduled corrective maintenance, where you're scrambling to fix something that has already broken, often causing delays and safety concerns, towards far more efficient planned maintenance.
Planning repairs instead of reacting to breakdowns.
Exactly. You can strategically schedule a repair during off-peak hours, or when a train is already scheduled to be in the depot for other routine checks, or maybe combine it with other planned maintenance activities on nearby components. It optimizes resources, minimizes disruption to passengers and freight, and significantly enhances overall network reliability and safety. This sophisticated approach means you're no longer reacting to a broken component, but intelligently planning its replacement or repair before it even becomes a problem, optimizing resources and minimizing disruption across the entire network.
Wow. This has been an absolutely incredible deep dive into the world of condition monitoring for railways. It's crystal clear that the combination of advanced remote condition monitoring, enhanced automated non-destructive testing, and this really intelligent data analysis is truly transforming railway maintenance from the ground up. It's about being smarter, safer, and just infinitely more efficient. It's almost like allowing the entire railway system to become remarkably self-aware of its own health.
Indeed. The intelligent trending and sophisticated analysis of this vast amount of data really empowers the industry to precisely identify those rogue components that are underperforming, accurately quantify degradation rates to understand how parts are really wearing in service, predict residual life to maximize component utilization, and ultimately develop these highly optimized proactive maintenance plans that, maybe only a decade or two ago were considered pretty much impossible on this scale. It truly moves us towards a future of proactive rather than reactive maintenance, minimizing downtime, extending the operational life of critical assets, and fundamentally enhancing safety for everyone who relies on the railway.
It really is like giving the entire railway network its own sophisticated digital nervous system, constantly sensing what's happening, analyzing the signals, and predicting potential problems before they arise. The sheer scale and complexity of this transformation are, well, mind-boggling when you think about it. But the benefits for both the industry itself and the millions who rely on it daily seem undeniable. So for all of you aspiring engineers listening, maybe future railway professionals, or just safety enthusiasts out there, as you think about the future of transportation and the hidden intelligence that's increasingly keeping it moving, what stands out to you most about this revolution in rail maintenance? What aspect seems most significant?
And building on that, perhaps this raises an important, more forward-looking question for everyone to consider. As these data collection capabilities continue to expand exponentially, which they will, and as analytical tools, particularly AI and machine learning, become even more sophisticated and accessible, how might they further accelerate our ability to achieve true whole system optimization across the entire railway ecosystem? Moving beyond simply predicting individual component health, could we realistically foresee predicting network-wide performance bottlenecks, optimizing traffic flow across the whole country in real time based on predicted asset availability, or even dynamically adapting operations to changing environmental conditions like extreme weather, all based on this predictive insight? Could this ultimately redefine what's possible in terms of efficiency, resilience, safety, and maybe even the fundamental passenger experience on our railways?
A truly fascinating thought to ponder as we wrap up today's deep dive. Where could this technology take us next? Whole system optimization. Wow. We really hope this exploration has given you a clearer, maybe more profound picture of how data and cutting-edge technology are steering the future of railway safety and efficiency. And perhaps it's inspired you to look at the trains running around you or the tracks they run on with a completely new understanding of the hidden intelligence that's tirelessly working behind the scenes to keep them running smoothly and safely.